Hello, and welcome back. We are starting a new unit today on parametric and polar equations. We're going to start our adventure in parametric equations. Today we will figure out, well, what they are. And of course, we'll be able to find the slope of a tangent line because this is calculus and that's what we do. And we'll solve some problems involving what we call planar motion. Up until now, you've been representing a graph by a single equation involving variables. Like this, consider the path followed by an object that is propelled into the air at a 45-degree angle if the initial velocity of the object is 48 feet per second. Then the object travels along the parabolic path given by this equation here. Y equals negative x squared over 72 plus x. However, this equation does not tell the whole story. Although it does tell you where the object has been, it doesn't tell you when the object was at any given point x, y. To determine this time, you can introduce a third variable, perhaps t, called a parameter. By writing both x and y as functions of t, you'll obtain parametric equations. So in this case, x equals 24 root 2 t. And this would be describing the horizontal motion. And then another equation would be y equals negative 16 t squared plus 24 root 2 t. And this would be describing the vertical motion. From this set of equations, you can determine that at time t equals 0, the object is at the point 0, 0. And then at time t equals 1, the point has moved here to 24 root 2 for the x value and 24 root 2 minus 16 for the y value. This original equation that we started with, that you're used to working with, is a rectangular equation. And then we split and add the parameter, well, those are called parametric equations. When we're working with parametric equations, this curve here that's been created, we call that the plane curve C. Now, when you're sketching a graph by hand of a curve represented by a set of parametric equations, then you can plot points in the xy plane. And each set of coordinates is determined from a value chosen for the parameter t. And by plotting these points in order of increasing values of t, the curve is traced out in a specific direction. And this is called the orientation of the curve. For example, make a table of values and sketch a curve indicating the direction or orientation of your graph. And then, this is interesting, we're actually going to eliminate the parameter. So if you look at this chart here, we've got various values of t, or time, that we're going to plug in. So we'll start with time t equals negative 2 and plug that in to the x equation, and you get negative 5. And then plug it into the y equation, and you get 3. So we have a point, negative 5, 3. And then we'll do that again for negative 1. Plug it in for the x equation, plug it into the y equation, and we have a second point. And we'll just continue this, paying attention to how the dots are being plotted on the graph. All right, so we have a line here. And as you were plotting, did you notice that the line was going in a downward direction? So we can put this arrow here to indicate that. Now the second part said to eliminate the parameter. Well, you can't just take it out, but what you can do is take the x equation and solve for t. Then take that t and plug it into the y equation. And when you clean that up a little bit, we have the equation of our line right here. Y equals negative 1/2 x plus 1/2. Isn't that cool? I love how that all works. Example 2. For t greater than or equal to 0, a particle is moving in the xy plane and is modeled by the parametric equations of, okay, so we're given two equations. X of t equals t cubed minus 3t squared minus 9t, and y of t equals t cubed minus 15 over 2t squared plus 18t. At what time is the particle at rest? Interesting. So what we need to figure out is, where do both x prime of t equals 0 and y prime of t equals 0? Now remember, x prime of t, that is the horizontal motion. So where is the horizontal velocity? 0. Y of t is vertical motion. So where is the vertical velocity? 0. So we'll start with x. Find the derivative. This is now the horizontal velocity, and set it equal to 0. Factor out a 3. Factor my polynomial. And we get t equals negative 1 and 3. Now, we don't care about negative 1 because we have a domain restriction up here. We've got t greater than or equal to 0. Now we'll do the same thing with our y parameter. So we'll take the derivative, set it equal to 0, and factor. And we've got 2 times t equals 2 and 3. So what we want is when the horizontal velocity and the vertical velocity both equal 0. So what they share is this 0 of 3, which means the particle is at rest when t equals 3. There's no horizontal velocity and no vertical velocity. Now, of course, this is calculus, and we love taking derivatives. So we're going to learn how to take derivatives in a parametric situation. If a smooth curve C is given by the parametric equations, then the slope of C at xy is. Okay, so dy dx is dy dt over dx dt as long as dx dt doesn't equal 0. That looks scary, but basically the derivative is y prime over x prime. Then, of course, we can also take a second derivative and a third derivative. Now, the second derivative looks scary, but it's not too bad because all we do is we'll take the derivative of the first derivative and then just stick it over dx dt again. And then the third derivative, well, we take our second derivative, take the derivative of it, and stick it over dx dt again. So let's practice that. A curve C is defined by two parametric equations here. We're going to find dx dt and dy dt. So dx dt, that is just the derivative of the x equation. So if x equals t squared, then dx dt is 2x. If y is t cubed minus 3t, then dy dt is 3t squared minus 3. We've got that. Now we want to find dy dx. Okay, well, that's easy because we just have to do our y prime over our x prime. And there we have our first derivative. Part C says, find the second derivative. Okay, well, let's go back here. We're going to take our first derivative and take the derivative of it. Okay, so we'll have to use the quotient rule for that. So here, up here, that's our first derivative. And we'll take the derivative of it using the quotient rule. And then put that just over dx dt again. So if you want to clean that up a little bit, we can do that. And we have a second derivative of 3t squared plus 3 over 4t cubed. Example 4. Given these parametric equations, x equals 2 cosine theta and y equals 3 sine theta, write the rectangular form by eliminating the parameter. Now before we were using a parameter of t, but this time our parameter is theta. So how do we get rid of it? This is a little bit crazy, so buckle up for this one. So we know that x equals 2 cosine theta and y equals 3 sine theta. So I'm going to divide both sides by 2 to get cosine theta by itself, and I'm going to divide both sides by 3 to get sine theta by itself. Now I'm trying to get rid of theta, but it's stuck. It's stuck inside the cosine and the sine. So here's a little bit of math magic. What I'm going to do, I'm going to square both sides of the parametric equations. Now, if you'll remember, we have this amazing trig identity that's cosine squared plus sine squared equals 1. So I've got a cosine squared here, and I've got a sine squared. So if I add those together, I get 1. And look at my theta disappeared. And I can sketch this on the grid here because that's the equation of an ellipse. Now, of course, we want the slope of the curve at a particular place. So to find the derivative, we'll just take y prime, that's 3 cosine theta, over x prime, which is negative 2 sine theta, and then evaluate it at pi over 3. So cosine pi over 3 is 1/2, sine pi over 3 is root 3 over 2, and we can clean that up a little bit, and we have our slope. And a calculus problem is not complete until we have the entire equation of a tangent line. Now this is a little bit interesting because we need, of course, point and slope. Well, we have the slope, we just found that, but to find the point, we need to plug our theta back in to find an x point and back in to find a y point. So 2 cosine pi over 3 will give us an x of 1, and 3 sine pi over 3 will give us a y of 3 root 3 over 2. And now we can have the equation of our tangent line. Example 5 says find all points, if any, of horizontal and vertical tangency to this curve given these two parametric equations. Okay, so tangency, that's going to be around the slope. So we need to find the derivative. So x prime is 1, y prime is 3t squared minus 3. So our derivative is y prime over x prime. Now, if we want horizontal tangency, that means that the top of our slope has to equal 0. Okay, we can find that. We'll solve for t, and we've got 2 times, positive and negative 1. So we need to use this to find our 2 coordinate points that go with that. So let's take negative 1 and plug it in to our x equation, okay? And we get 3. And then we'll take negative y and plug it into our y equation, and we get 2. So we've taken care of negative 1. Now we need to do the same for positive 1. So plugging in 1 to the x equation gives us 5. Plugging in 1 to the y equation gives us negative 2. So there we have our 2 points of horizontal tangency, 3, 2, and 5, negative 2. It also asked us about vertical tangency. And vertical tangency is whenever the bottom is going to be 0, the bottom of the slope here. But that's just 1. It's never going to be 0. So we don't have any places where there's a point of vertical tangency. Now, interestingly enough, I plugged this all into my calculator, and you can plug in parametric equations by going to the menu and switching to a parametric mode. And then if you go back to your equation editor, you can plug in the x equation and the y equation and then graph it. But this was what was interesting to me was that I had points of negative 1 and positive 1 before, but they're not showing up here. So what you have to do sometimes is go back and check the window and look at what it had. It had a t minimum of 0, which makes sense because often we start with time equals 0, but in this case we didn't. So I went in and just expanded the window a little bit and made sure that t could go, well, into the negatives. Then when I graphed it, aha, now I've got the whole thing. So that worked out much better. Okay, I think this is the last one. Determine the t intervals on which the curve is concave up or concave down. Now, concavity lives in the second derivative, right? So we have our two parametric equations. To find the first derivative, we'll take y prime over x prime. And let's see, we can make that into a negative tangent t. And then to find the second derivative, we have to take the derivative of that, which is negative secant squared, over x prime again. Clean that up a bit. We've got negative 1 over cosine cubed t. Next step is to find the critical point. So cosine cubed t equals 0 at pi over 2. So that's my critical point. So we'll put a little picket fence together here. And to the left of pi over 2, if I plug in maybe 0 or something, I have a negative double derivative. If I plug in something greater than positive 2, I have a positive double derivative. So I've got concave down up until pi over 2 and concave up past pi over 2. So we know that our graph is concave down between 0 and pi over 2. And it's concave up from pi over 2 to pi. So we've covered a lot, but actually a lot of it's stuff you already know. So if you think about it, you kind of just get 2 problems in one every time. More calculus, that's so fun. Okay, I'll see you next time.